Good day, we are reviewing Wetzel's Limnology textbook. This is edition number 4 and we're in chapter 8, water movements, and today we'll be looking at surface sèches as example of long-standing waves. So let's get started. Surface sèches are example of long-standing waves produced in response to winds. Gravitational adjustment to water that accumulates at one end of the lake leads to flow toward the other. That is, an oscillatory motion develops with a node in the middle of the lake. These waves affect the entire water mass of a lake, regardless of whether it is stratified, and have their largest amplitude displacement at the surface. In most cases, the amplitude of surface sèches is small, in the order of millimeters. Occasionally on large lakes, such as Lake Geneva or Lake Erie, amplitudes can be 1 or 2 meters and serve to flush river delta and harbor seas. Surface sèches have been known since at least the 19th century. For example, Forel noted them in Lake Geneva. Flows from surface sèches were one of the first wind-induced motions recorded under ice in winter. The sèche period in a well-mixed lake, it can be calculated as T is equal to 2 over L over the square root of G by the average of the square root of G by Z, and Z is the average of the mean depth, where T is the wave period, L is the length of the lake along its axis, and Z bar is the mean depth. Reported periods are on the order of 26 minutes in Lake Mendota, 73 minutes in Lake Geneva, and 14 hours in Lake Erie. Langmuir circulation or Langmuir cells are often evident on the water surface as windrows once winds exceed 3 meters per second. Vertical counter-rotating helical currents form perpendicular to the wind direction. Areas of convergence and divergence are visible at the water surface, with light organic material and foam accumulating and forming coherent streaks in convergent zones. The streaks are aligned parallel to the wind at the water surface, with the helical motions below. The spacing between streaks is usually about twice the mixed layer depth in stratified systems. Langmuir cells result from the interaction of surface waves with wind-driven surface currents. They are sometimes considered an organized form of turbulence capable of transporting appreciable momentum downward. However, many questions remain as to their contribution to mixing in the surface layer. Influence of the Earth's rotation on surface current and effect of stratification. The Coriolis force due to the Earth's rotation causes currents to be deflected relative to the direction of the wind. With respect to surface currents and the formation of gyres, the influence of the Earth's rotation can be determined from the Rossby number. Rho is equal to U divided by LF, where U is the characteristic velocity, L is the basin dimension, and F is the Coriolis parameter, which varies with latitude. Rotation is important for small values of the Rossby number, less than 0.2. For example, for F is equal to 10 to the minus 4 by second, as at latitude 45 north, a medium-sized lake with L of 5 kilometers and assuming surface currents of 0.1 meters per second, rho is equal to 0.2, indicating an influence of rotation on surface currents. Inertial currents are those influenced by rotation. The combined effects of wind and geostrophic deflection cause surface water to move downwind and to the right in the northern hemisphere and to the left in the southern hemisphere. The direction of the wind in a spiral manner, the Ekman spiral, in open waters of large deep lakes. As the size and especially the depth of the lake decreases, the magnitude of the deflection angle decreases until in a lake with a depth of less than 20 meters, the angle of declination becomes insignificant. When considering rotational effects within stratified lakes, the internal Rossby radius of deformation, Ri, must be smaller than the basin dimension. The equation for the Rossby radius accounts for the Coriolis force and the phase speed of the internal wave C, and the rate at which a wave propagates, which depends on stratification. The internal Rossby radius is calculated at L1 or Li is equal to C divided by F. In a two-layer lake, that is, one with an epilimnion and a hypolimnion and a sharp discontinuity between them. So C is equal to G by rho 1 minus rho 2 in parentheses, Z1, Z2 over the square root of rho 0 by the power of Z, where, or by Z, I'm not sure, probably by Z. Where Z is the depth of the lake, the hypolimnion would have depth Z1 and density rho 1, and the epilimnion would have depth Z2 and density rho 2. Giving a positive value for C and the mean density, for example. For example, in 150 kilometers squared mono lake, Li or L1 was 8 kilometers based on the stratification in 1995, just less than the length of the lake at the depth of the thermocline. Hence, internal waves were expected to be affected by rotation, with three-dimension 3D hydrodynamic modeling subsequently proved to be the case. Gyres. The surface currents of moderate and large lakes often have large swirls known as gyres. Lake Michigan, USA, for example, is typically exposed to predominantly westerly winds during summer, and its large conspicuous gyres are clearly influenced by geostrophic rotational forces. Gyres in lakes the size of Lake Michigan are not simply the result of geostrophic forces. Their direction is strongly modified by large, long waves, and especially by shifts in the direction of strong prevailing winds. Similarly, Lake Biwa, the largest lake in Japan, has 3 counter-rotating gyres that have been observed by ADCP measurements. In lakes of all sizes, gyres may be induced due to promontories and other irregularities along their coasts or spatial differences in the wind speed and direction that lead to the swirls. Excellent examples of gyres in lakes with and without the influence of rotation are provided. The movement of gyres can be complicated by other water movements such as internal waves. The geostrophic right-hand acceleration of currents also occurs under ice cover even in small lakes due to weak stratification under the ice. Consequently, gyres can form under the ice in mid-sized lakes and large lakes such as Lake Baikal. Wind-driven motions in the interior. As wind induces surface currents, it displaces water downwind. The resultant pressure gradient causes the thermocline to tilt, and the shear induces Kelvin-Helmholtz billows and mixing between the upper and deeper layers of the lake. Internal wave motions. The onset of wind causes the thermocline to tilt, which already know that. On relaxation, as surface water flows in the opposite direction, the thermoclines begin to tilt in the other direction. Okay. So let's look at this here, figure 8-20, wind-driven surface currents and associated tilting of the thermocline as surface water accumulates downwind in the northern basin of Windermere in the UK. In this conceptualization, Windermere is divided into an upper mixed layer with the hypolimnion below, panel A to C. So what we have is we have the epilimnion here, or the mixed layer, and then the hypolimnion here. Okay, and then we have then a tilting occurring here, and that the wind is going from left to right. And so once again, the arrow's head shows the direction of the currents, and the length of the arrow shows the dimension and the magnitude of the velocity in this case. Let's see. So the magnitude of surface current is indicated by the length of the arrow, which currents are highest at the surface. So yeah, we can see that the currents are the highest at the surface. They induce downwelling and a return flow above the thermocline. They also induce flow in the hypolimnion. Indication of speeds and direction of flow are indicated by arrows. In the example, the wind is strong enough and was persistent long enough to induce considerable upwelling of the hypolimnictic water, as can be seen in D. So what we have here is we have upwelling of this colder water in the left side of the lake here. Upwelling in the cross basin and temperature, depending. The curved arrows in B are indicative of shear-induced mixing. So this is shear-induced mixing here with the curved arrows. Mostly Kelvin-Helmholtz billows. These combined processes occur when Vandenberg numbers are low. Okay. Due to its inertia, the thermocline continues to upwell and downwell at successive ends of a lake basin. This continuous rocking back and forth of the thermocline is known as seiching. The up and down motion of the seiche and its maximum amplitude at the lake margins, the antinode, and minimal vertical movement at the node. Seiches are standing waves, that is, they do not travel and are generally classified as a type of linear internal gravity wave. Internal waves can also be classified as progressive, meaning that they can travel across a lake, transporting energy. Such waves can also steepen abruptly, similar to the steepening of wind-induced surface waves prior to their breaking in the near shore. Such waves are classified as nonlinear and may contribute to mixing within a lake. The thickness of the thermocline and the stratification across it moderates whether internal wave modes are first vertical mode, or higher degree second or third mode. When the thermocline is relatively thin, as its first forms in spring or after storms, first vertical mode waves typically occur. Here, the upper and lower boundaries of the thermocline remain approximately parallel. As the thermocline thickens, it can support higher order internal waves. For example, in the second vertical mode, internal wave, the thermocline spread at one end of the lake and compresses the other. As the thermocline oscillates, the compression and spreading alternate between the sides of the lake. Second vertical mode waves are common within the metalimnion of Toolik Lake in summer. Frequency analysis shows that the internal wave field is comprised of a composite of these wave types. Seiche periods can be calculated from the length of a lake and the phase speed, as t is equal to 2L over C, where C is given by C and by this formula. For the first vertical mode internal seiche, the periods of higher mode internal seiches can be computed considering the density stratification throughout the water column. As the thermocline upwells and downwells across a lake, shear develops across it, which leads to mixing. Spiegel and Himbenberger developed a quantitative scheme based on the Richardson number and basin morphometry to illustrate how the extent of tilting of the thermocline, the density difference across it, the depth of the upper mix layer, and the length of the lake would moderate shear within the thermocline and the extent of mixing within a lake. This conceptualization formalized to the Vandenberg number, W, and later extended to the lake number. Ln has led to a quantitative understanding of control of mixed layer deepening, the contribution of internal waves to mixing within the thermocline, and to exchange between the epilimnion and hypolimnion. This is a very long sentence. Probably would have helped. It was a little bit broken up. But anyway, let's move on to figure 821 here. Movement caused by I, wind stress, and II, a subsequent internal seiche in a hypothetical two-layered lake, neglecting friction. Direction and velocity of flow are approximately indicated by arrows. HE and HH are depth of the epilimnion and hypolimnion, respectively, and L star is approximate basin length. So, we're starting here, and so the wind begins from left to right, and so it's basically kind of like a hypothetical like seiche, and how the seiche developed on a lake that is stratified, and that has an epilimnion here and then a hypolimnion below. And then so tilting is occurring, and so there's negligible flow. So this is the return. So you can see a deepening of the tilting. Now the wind stops, so there's no flow. Then there is it appears in D, it goes back to its equilibrium, which is right here, where we have an epilimnion and a hypolimnion, and this is a thermocline. And then we have the reverse occurring. So this is what, how a seiche is generated, is a sort of oscillation within the entire basin that first started by wind. So it goes this way and then it goes that way. It oscillates between the two sides of the lake. Let's see. Laboratory experiments illustrated the extent of mixed layer deepening for different values of W. For W less than 1, results indicated compression of the thermocline downwind and its expansion upwind, as in Windermere in figure 820-D. This motion is not the result of a second vertical mode internal wave, but is instead from shear at the density interface, resulting in the direct exchange of water from the hypolimnion into the epilimnion and considerable mixing, similar to the observation in Tulip Lake. Field experiments illustrated that when W dropped to 2, sigma and Kz were calculated to be 3 to 4 orders of magnitude higher in the thermocline near shore than offshore. The mixing was enhanced by internal wave breaking near boundaries. Tracer experiments similarly indicated the enhanced mixing near boundaries. The Vandenberg number also predicts the type of internal waves that result as they steepen and become nonlinear. Surges and solitons, solitary waves, occur for Vandenberg numbers in a range between 1 and 5. The steepening of the thermocline is called a surge, and a packet of solitons form in its rear. Laboratory experiment and modeling indicate that the solitons will break at the lake margins and cause mixing. For larger wind forcing relative to stratification, internal waves become nonlinear. In the Kelvin-Helmholtz regime, the progression begins with a tilted thermocline and is followed by internal bores, a highly nonlinear internal wave, forming on both ends of the thermocline, horizontal movement of the bores inward from the margin, and with increased shear of formation and instability of the Kelvin-Helmholtz billows. This intense mixing from a wind event that induced these features in Lake Cayuga was illustrated using 3D hydrodynamic modeling. Fluxes of solutes and particles from the sediments may additionally result from the interaction of the nonlinear internal waves with the boundary. Mixing near the boundary of lakes is also caused by near-bottom currents induced by seiches, not necessarily due to the breaking of internal waves. Okay, so why don't we look at these two figures and we call it a day for today here. So this is figure 8-22, horizontal, so A is horizontal surface seiche identified by the change in the surface elevation. So the epilimnion, the metalimnion, and hypolimnion, and we have a seiche here. So we have this oscillation. B, first horizontal V1H1 seiche in which the thermocline thickens is the name as it upwells and downwells. The upwelling and downwelling occur relative at a stationary node in the center of the lake. So there's like a center node, basically, pretty much like the center of mass of the center of volume of the lake right here. C, first vertical, second horizontal V1H2 seiche in which again the thermocline thickens, does not vary across the lake, and the up and downwelling is relative to two new nodes. So now we have this secondary horizontal seiche here. So instead of having like a diagonal, we have like a diagonal this way and then diagonal that way. So it's relative to two nodes. So we have also the presence of probably two nodes, probably a node here and a node here. And then D, second vertical, first horizontal seiche in which the thermocline alternately compresses and expands at each end of the lake as the thermocline upwells and downwells around one node. So here we have the thermocline thickening and then the thermocline thinning. And it's the first time where we have a change in the thermocline relative to its magnitude across the lake. Usually they're pretty even across the lake. Figure 8-23. This is the phase space illustrating whether linear or nonlinear wave will form in a lake as a function of the inverse of the Vandenberg number, 1 over W, and the depth of the mixed layer, H1, over the depth of the lake basin, H. Linear waves. So here we have H1 over H, depending on H1 over H, which is H1 is the mixed layer, and H is the depth of the basin. So the mixed layer divided by the depth of the basin. And then here we have 1 over W, 1 over the Vandenberg number. So therefore, for example, let's say that we have a H1 over H of 0.4, and we have 1 over W of 1.5, we're in the bores and billows, and we have internal bores for H1 over H are less than 0.2, but for 1 over W greater than 1.5. So it kind of tell us whether we're going to have linear or nonlinear waves here. And then the last figure is evolution of a nonlinear internal wave, N1 NLIW packet with the initial wind-induced depression of the thermocline. So we have a depression of the thermocline that was wind-induced right here. Very likely the wind is coming from the left and going to the right. And B and C, development of a surge. So we have a surge development here, a surge on this side, and C. And D and E, further evolution with the surge and solitons. And solitons are like solitary waves. I believe that's how they define that. Yeah, solitary waves are predicted for 1. So let's see here. And so it's depending on the slope of the bottom boundary, these may be reflected or become unstable and break, causing mixing at the boundary. Okay. All right, so I think that's going to be about it for today. And tomorrow we'll be looking at, well, actually there's still this figure. Why don't we look at this figure before we close off? Model results illustrating thermocline tilt and the formation, thermocline tilt right here, and B and C are the formation of internal bores, okay, at the lake margins. All right. We have a bore here and I think a bore there. And D and E, subsequent formation of Kelvin Helmholtz bellows. So these are the bellows in the thermocline due to strong shear that develops. And F, their collapse and mixing. So we have the collapse of the Kelvin Helmholtz bellows here, right here. All right, that's it. Tomorrow we'll be looking at the influence of the Earth's rotation on internal waves, Coriolis forces. Thank you and talk to you soon. Bye.